Hi, we are NovaDrop. We'll be sharing about our project in creating a decentralized Dutch auction platform built on the Ethereum chain. So our main objective in this project was to launch a new ERC20 token using a Dutch auction model. Unlike a traditional auction where prices go up, in a Dutch auction the price starts high and decreases over time. This ensures that all participants who buy the token end up paying the same final clearing price. So essentially, the goal was to create a fair, transparent, and decentralized token distribution process on Ethereum. To achieve this, our project included several key components. First, we developed the ERC20 token contract itself. Next, we implemented the Dutch auction smart contract, which controls the auction duration and manages the price reduction across the 20-minute time window. At the end of the auction, the contract automatically distributes tokens to eligible bidders at the final price. If there are any tokens left unsold, the contract burns them, meaning they are permanently removed from the total supply to prevent inflation. We also tested the system against reentrancy attacks to demonstrate security against common smart contract vulnerabilities. So for the project design, we kept both the front-end code and the smart contracts together in a single unified code base. This makes the development process more consistent and easier to maintain. There are two main advantages. First, consistent tooling. Since everything is in one environment, we only need one set of dependencies, one testing setup, and a single build process. This reduces complexity and makes the workflow much cleaner. Second, streamlined development. By using the same setup across the entire project, the team can collaborate more efficiently. It also speeds up development time because we don't have to manage separate environments. Overall, this unified project structure helps ensure our development process remains smooth, organized, and scalable.
The project allows for a monorepo architecture that separates the front end, smart contract, and shared UI components while allowing for unified version control and easier deployment. The web module, built with TypeScript, WAGMI, and Rainbow Onchain Kit, handles wallet connections and user interactions directly from the browser. The Node module contains the Solidity, smart contracts, and hard hat environment used for compiling, testing, and deploying the auction logic. The Components module holds reusable TypeScript and Tailwind CSS UI components shared across the project. For deployments, the front end is hosted on Vercel, ensuring fast global delivery, while the smart contracts are deployed on Base Sepolia, a layer 2 Ethereum test network optimized for low cost and high speed transactions. This setup provides a seamless bridge between a performant user interface and a scalable blockchain backend.
So I'll walk you through the smart contract architecture behind our on-chain auction system. Our system is composed of three main Solidity contracts: auction.so, which is the core auction logic; auction factory.so, which is the manager that creates and tracks auctions; and lastly, the test token.so, which is a custom ERC20 token used within the auction. So let's go through each one of them. Auction.so is the heart of the platform. It handles the entire bidding process from start to finish. It accepts bids from participants and keeps track of how much each user has committed. Once the auction ends, it calculates the clearing price, determining the final token price that balances the supply and demand. After that, it distributes tokens to the winning bidders based on their contributions and refunds any unspent funds. It ensures a fair, transparent, and automated auction process on chain. The auction factory is the auction manager which controls and registers for all auctions. It deploys new auctions and tracks all active and completed auctions so users and front end can easily discover them. The test token also is a custom ERC20 token which is used in the auction. It implements the standard ERC20 interface for token transfer and balances, supports minting and burning, and allowing the system to issue new tokens for auctions or destroy unclaimed tokens. It provides the digital and fully compatible with ERC20 wallets. So for functions in our auction.so, we'll go through these three main functions. For the finalization function, can only be called once and will only by the owner of the contract. It's protected by the non-reentrant modifier to prevent reentrancy attacks. It will distribute tokens and refunds to all builders and will burn any unsold tokens and withdraw the auction proceeds to the owner. So it will starts by checking two conditions to make sure that the auction hasn't already been finalized. Once those checks has been passed, it marks the auction as finalized so it can't be called again. It will then look through every bidder who participate in the auction and then it will distribute the tokens and refund accordingly. This ensures that every participant automatically receives what they are entitled to and no manual claims are required. Then it will burn unsold tokens that are remaining. Then it will withdraw the remaining ETH left in the contract and is being forwarded to the contract owner. Lastly, it will then emit a finalization event to just tell how many tokens were being burned and how much ETH was being forwarded. The current price get current price function will give the live prices, and for the commit function is basically when users bid how much they want to bid for.
This slide covers reentrancy, a vulnerability where a malicious contract keeps calling a function before it finishes executing, potentially draining funds or breaking logic. To prevent this, we use two main safeguards. Firstly, non-reentrant modifier from OpenZeppelin's reentrancy guard, which locks functions like claim and finalize during execution to block any recursive calls. The checks effects interactions pattern, where we always update the internal state before transferring tokens or Ethereum. So even if an attacker re-enters, nothing changes. We then built a comprehensive test suite in Hardhat to simulate these attacks. Using a custom malicious bidder.sol contract, we ran 13 reentrancy test cases against all major functions: commit, claim, batch claim, and finalize. Every attack attempt was blocked. 13 out of 13 tests passed, confirming that each bidder can only settle once and that no double claims or Ethereum drains are possible. In short, both our contract design and testing suite prove that the auction is fully secure against reentrancy exploits.